Hello and welcome to GoEngineer's webinar on the Origin 1. Really excited to have you with us today. We're going to be talking about end-use parts that can be created using high-performance photopolymers. We have about 20 to 30 seconds and then we will begin. My name is Hunter Bernstein. I am an additive manufacturing application engineer, and we are also joined with Tom Lopez from Henkel Adhesives. Tyler Reed, the digital manufacturing technical director at GoEngineer, will be assisting in this webinar, answering questions and relaying any questions the audience may have. If you have a question during this webinar, please type them into the chat. We will address them as they come up, and there will also be a section at the end. This webinar will be recorded and posted later for you to review. Thank you. Let's get going. GoEngineer provides design and manufacturing tools with expertise that enables customers to reduce their cost, risk, and time required to go live with new technologies, ultimately leading to new product introductions. GoEngineer has locations all across the United States, and we are also the #1 resource for SolidWorks and Stratasys machines. Here is a map depicting all of our locations across the United States. We are currently in the Salt Lake City office, where the Origin 1 is today. Today's webinar will feature the Origin 1 features in operation, the available materials and mechanical properties. We are going to look at some case studies and proven applications of the materials, along with when to consider using an Origin 1 in your industry. We're going to wrap things up by comparing the Origin 1 to existing DLP and other resin machines that are on the market today. So with that, let's dive right in. The Origin 1 features a very unique printing process. This process is called P3, or Programmable Photopolymeric Technology. What this enables is very, very precise control over the exposure time down to the 1,000th of a second, and your speeds, your delays, the separation forces, and the temperatures within the printing environment. There are over 20 sensors in the machine that are monitoring all critical printing process parameters throughout the cycle of a print. Right now I have the machine open, and so you can see a print taking place. I'm going to show a very short video where we actually break down the P3 photopolymeric technology. The first step in this is applying a pneumatic separation system. What this system does is sucking down a membrane to create a very, very tight seal against a projector screen. A cross-sectional area of the printed model is then illuminated on this screen. The photopolymer cures where the light is illuminated. The pressure is released and filled with a positive pressure, creating a bubble within the vat. This reduces the printing forces substantially, enabling very large cross sections and very small features to be printed without the risk of parts becoming damaged when they are removed from that lower membrane. Now, I would like to show a video of this printing process in action. On the right hand of the screen, you will see the real-time analytics that the printer is monitoring throughout this printer process. Enabling this, the Origin 1, is a 4K DLP projector. A DLP projector works with a high intensity light source that gets concentrated onto a DMD mirror. This DMD mirror has independent electrically controlled mirrors for each of the pixels. This is then enlarged to display the image across the lower membrane of our printing vat. The Origin 1 uses single part resins, meaning there is no mix required before you start printing. This vastly increases the shelf life of your resins since you no longer need to mix two together. When you mix two resins together, a chemical reaction begins to form that requires use within 8 to 12 hours. The vat has a perimeter heater that is also monitored by an infrared camera. This ensures that the resin is always at the proper temperature throughout the printing process. The chamber itself can become fully inerted and devoid of any oxygen. This enables printing with different chemical compositions that elsewise you cannot be using. In addition to that, the exhaust system on this is suitable for a production and an industrial environment. You are able to directly route this into your central exhaust system that you may have pre-existing in your facility. The build volume is 4.5 inches by 7.5 by 14.5 in the Z. This is quite a standard size for DLP machines, giving a perfect blend between resolution and part size. The Origin 1 uses a 385 nanometer UV light source to cure the resin. That projector has a XY resolution of 50 microns, or 2,000th of an inch. The printable layer heights are between 25 to 200 microns, enabling extremely fine features and precise control over the accuracy of your models. The vat has a 2-liter capacity, enabling large parts to be printed with an extremely high throughput. So now I'd like to look more in depth onto the inside of this machine and cover some of the sensors and monitoring systems in place. We're going to start up at the top, looking at the build head, where we have some load sensors that measure the printing force being applied to the part throughout every moment in the printing process. This enables real-time feedback and closed-loop control, verifying that your parts are not being put under too high of a force environment. We have a humidity sensor and a pressure sensor that is monitoring the ambient environment within the machine itself, and a few IR cameras mounted throughout the machine. These IR cameras can be accessed real-time on the printer UI and also post-printing, so that you can go back and analyze any print logs that need to be assessed. Additionally, further implementations will be made, enabling real-time viewing of these cameras on the web app. We have a UV energy sensor inside of our tank that verifies the UV projection light is working as intended and putting out the proper light intensity for each of its layers. There are pressure sensors inside of the pneumatics to enable fine-tuning and precise control over positive and negative inflation pressures. This is critical in maintaining high surface quality and high speed throughout the printing process. There is also a temperature sensor monitoring the resin temperature throughout the print process. You have a liquid sensor in case of any type of spill or leak within the system. It will automatically detect this, stop the print, and ask the user to verify there is nothing wrong with the machine. This is a great safety feature that prevents any long-term damage to the machine. When working with the Origin One, it's not as straightforward as an FDM. It requires a little bit more. As you can see, I have my safety glasses on, a lab coat, and some gloves. This is all required when working with hazardous liquids or materials. Some optional equipment would be a fireproof or an explosion-proof cabinet to store any of your solvents or resins, and a lab fume hood for post-processing. Now, I say these are optional because it depends on your state law and how your facility is already set up. Here in our Salt Lake office, we have quite a large lab with good ventilation, so we are able to keep our machine freestanding in the room. We do not have a lab hood or any direct fume extraction connected to this machine. If you were in a brand new environment, this might be something of interest, but I recommend you to always take proper safety precautions, read into your local laws, read the MSDS before you proceed with working with any type of dangerous material. And with that, I would like to actually jump a little bit more in depth to the machine itself. So up top here is one of the IRs. We have another IR on the left and a regular camera directly below. There's only one moving component on this machine, and that is the Z stage. This makes maintenance extremely easy and simple. You have a couple fan filters that need to be replaced and lubricant on the Z stage once yearly. Setup of this machine is a breeze. As soon as you receive it, you will install the main build head, loosen one bolt, and begin a calibration procedure. Unfortunately, with the machine printing right now, I cannot walk you through it. However, I can post this or follow up with anyone who may like to see it. Inside the printer UI, it will walk you through with displayed videos and step-by-step directions on exactly how to be calibrating this machine. Setup in first print should be about 20 minutes, and it requires no experience. You can have never touched a 3D printer in your life, be able to set up a print, walk away, and know that it will work. The reliability, consistency, and accuracy out of the box is outstanding. Also, the ease of use that Origin has incorporated with the simple UI and analytics screen makes it very intuitive for a new or an experienced user to dive right in and really get going on that. I'm going to jump this over to the Analytics tab for just a moment so that you can sort of see how many available tabs are are here. Currently today, some are being used for closed back control with the intent of further expanding and implementing all of these parameters to give extremely precise control over the machine as time goes on. They will continue innovating and adding more process parameters to maintain the best prints available. In about 7 minutes, this print will wrap up, and I will actually go ahead, pull it off. I'm going to take this vat out and show you how quick and easy a material change is. So you can start in the morning, be printing in material A. Halfway through, afternoon, like it is right now, switch over to material B. And then at the end of the day, right before you need to go home, switch back to material A. Or C, you can be exchanging materials throughout the day in a very quick and easy process. To what would be the right on the screen, I have a UV cure chamber. This is used to cure the parts after they come out of the machine and they have been washed. Typical wash time is about 5 minutes, and then you need to wait about 10 minutes to 1 hour for that part to dry. If you do not wait for that part to dry, it might have some residue that will show up white in the chamber. Very, very thin walls have a tendency to swell up. By letting them dry out, they will return back to their normal shape before cure. After waiting 10 minutes to an hour for that initial dry, throw it into the cure chamber for about 5 to 10 minutes, and your parts are good to go. They can immediately be put into use without the need for any thermal baking or additional post-processing. This is huge when you compare it to other competitors like Carbon or Nexa. Carbon requires an 8-hour thermal bake for most of their resins, and Nexa can require up to a 2-hour UV cure before you can put your part into use. The Origin 1 has an extremely high part green strength directly off of the machine. This enables shorter UV cure time and also less support material to be put onto your part, reducing the post-processing time. The materials that this machine offers are extremely high performance end-use engineering materials. So the Origin 1 uses an open material ecosystem. And I would like to clarify what this means directly. An open material ecosystem enabling partners to create materials for verified and certified uses on the Origin 1. Stratasys realized there are too many photopolymer compositions for them to really master and figure it out on their own. So they decided to open it up and partner with DSM, BASF, Henkel, and additional partners to come. This allows large OEM chemical manufacturers to be creating and designing photopolymers at the highest and peak performance available today. What this also means is any customer that would like to develop their own material has the option to do so. If they have a very specific use case where they need high tensile strength, high stiffness, very, very low elongation, and sterilizability with easy post-processing, these are all parameters that can be tuned for and designed for into these materials, opening up a new landscape of manufacturing and what is possible today. There are currently 5 photopolymer categories that are available to purchase. These consist of elastomers, some general purpose engineering materials, high heat resistance, high toughness and strength, along with medical. I've prepared a chart for us to look at where we can compare the heat deflection temperature against the elongation or stiffness of these materials. The further out on the x-axis, the more flexible a material is, and the larger the circle is representative of a higher ultimate tensile strength, or the fracture breaking strength of that material. Looking at the bottom, we have 403. This is a great all-around engineering material that's been used in molding applications and high heat, well, moderate heat applications. 3955 is really used in high heat applications with a heat deflection temperature exceeding 300 degrees Celsius. This is extremely high, giving it room to be used in a lot of different industries. Additionally, this material has a flame, smoke, and toxicity certification. It can be sterilized and used in chemical environments. We have some very tough materials that are resilient to impact strength and feature very high torsional stiffness. 3843 and 3172 are awesome materials. They print really well, and they provide a really good mix of general mechanical properties. Dura 56 was developed as a low-cost alternative for these high-performance photopolymers, enabling rapid prototyping before you start production. We have some general purpose engineering materials that kind of fall in the middle. There's a healthy blend of strength, flexibility, stiffness, and temperature resistance. Additionally, these materials have been UV tested, weather tested, chemical tested, and some have been cytotoxicity or biocompatibility tested. As we move along, we have some elastomers that are very unique to the DLP market. Unlike Agilis, that has a low durometer, but not an energy return or rebound that you would expect from a silicone type material, we see true elastomeric behavior out of EL 150 and IND 402. These have extremely high rebound and extremely high elongation of break. This provides real soft touch and flexibility that elsewise was unachievable. To round things off, I've included some of our conventional manufacturing materials that you and I are more familiar with. Looking in the bottom left-hand corner, working to the right, we can see acrylic, ABS, Delrin, polypropylene, and polycarbonate. As it stands today, there is no one-to-one match for any of these materials, but that does not mean that will not come in the future. In fact, there is a lot of innovation and research continually being done in this sector. It is the largest growing additive manufacturing polymer division, meaning we will continue to see innovation for years to come with tuned materials for very, very specific intent and end use cases. I have another chart here, similar to the first, comparing the yield strength to elongation at break. As we look from left to right, we can see that we have very high stiffness polymers working into more flexible and energy absorption materials. 3172 has an extremely high impact strength of over 70 joules per meter with an elongation of break at over 100%. This material is great for extremely high energy absorption applications where it will just get beaten up. Dura 56 is a lower cost alternative that also has a very, very high elongation at break, but quite a high stiffness. This enables it to be used in a large variety of applications, ranging from prototyping to end-use parts. The medical resins are specifically formulated to be put into a medical type environment. This is not to say that you can only use a Med 413 or a Med 412, but these materials were designed and will work much, much better in a medical environment than ST45, for instance. ST45 can be sterilized. It does have a cytotoxicity rating, but that was not the original intention of developing that material. When you develop a material with a specific end use, you are able to tune the mechanical properties to precisely what you would like to achieve. This also enables very, very low bacteria formulation or growth and high sterilizability and cytotoxicity compatibility. Now, I have Tom Lopez present, and Tom, I was wondering if you have any input as to where we are going with these materials and where we should anticipate seeing more color up here.
Excellent. Thanks for the introduction. My name is Tom Lopez. I'm Business Development Manager for Loctite 3D Printing. Many of you probably know the Loctite name from being the largest adhesive manufacturer in the world, but we have a vast experience with photopolymers, creating adhesives that cure with UV light. That was our entrance into this. And so we've been producing these polymers for about 5 years now. And our goal has been to produce open source, which is very important, open source materials that have end use, very unique functional properties, right? As Hunter mentioned, 3955 with a very high HDT and FST, fire smoke toxicity rating, all the way to elastomers, materials we call photoelastics, which are very hard to 3D print. But where's this going in the future? We're currently innovating at an incredible rate of speed. When we first got into this marketplace, we produced a few materials of our own. We realized that we needed a little more horsepower, so we bought the most innovative polymer company on the planet called Molecule Corporation in the Bay Area, California. Molecule has a long history of probably anything that made the market or made the news with photopolymers. They were behind the R&D of that. So this is now a Henkel facility, and we have all of those engineers hard at work producing materials that are stretching the bounds of what's out there. And what's unique about the Origin platform is they've built in some features that enable the future of photopolymers. You know, obviously you need light at the correct wavelength, but you also need the right intensity of light. So a lot of people will say, hey, LCD is out there, it's less expensive, but it's really not nearly as intense of light. To drive these applications, you need that high intensity DLP light source, but also the correct wavelength at 385 nanometers. But back to the Origin 1, it has the built-in capability of being able to print at higher temperatures, up to 60 C. Now 3955, our FST material, has a very high HDT approaching 300 C heat deflection temperature. In order to achieve that, the material is solid at room temperature and must be printed after it's been liquefied. So it needs to be heated to 60°C and then printed at 60°C and then cured in a specific way as part of post-processing to get those properties, right? And so there's a little more work with respect to that, but really there's no other printer on the market that has the ability to print at a high heat like that, right? Now, Origin, seeing the future with the Stratasys Origin, they've also incorporated the chamber to do other things, such as being sealed, and maybe the future of polymers would be printing with a certain type of gas to achieve certain properties. You have to really think outside the box when you're engineering these unique and functional materials. Now, yes, we've got a lot of materials on the roadmap that are available now. However, Stratasys, we have a lot of these materials that have not been validated on the Origin platform as of yet. They're already commercialized, but those will be coming soon. So we expect additional materials to show up on the platform regularly. And again, we're innovating regularly. But there's one thing that we like to share is we're a very agile company, Henkel is. And should an application come up that requires a unique material or something that isn't available, or even a color change, if there's a strong business case for it, we can adopt that and really react quickly. So we're not talking years of development. We're talking fast tracking materials, even having samples in weeks out of our R&D house. So jumping back to where I started this out with a little story of Molecule. Molecule, the company we acquired in the Bay Area, worked with Origin from the beginning. Origin was based in San Francisco and still is, but they worked very closely together to develop a lot of these materials. And, frankly, in all honesty, which that's all I can speak to all the time, is our materials will run on a variety of different platforms, but there is nothing on the market like this Origin printer. It's the most glamorous, it's the most sexy, it's the most capable printer that's out there. And we're super excited that Stratasys has purchased this company and is offering this, because this is really going to change the future of additive. So I better cut myself off there because I'll talk all afternoon. Thanks for having me, and I'll be around to answer questions if there's time. Thank you.
Thank you, Tom. That was great. Thank you for the insight. Really happy to hear that you guys love working on this platform, developing the materials on this platform, and that it's outperforming the competitors on the market. Thank you for providing that insight. Really insightful information. So I do need to got to start running here, running out of time, and I don't want to keep anyone after. But let's start diving into these use cases. This 3955, we've talked about it for a little bit, but what actually is it? Where can it be used? Why should it be used? The United States Air Force was actually struggling. They had to replace a lot of hydraulic clamps for F-16s that are currently on the field and in use today. But machining these parts and making them out of conventional materials wasn't a practical option. The phenolic material that they were using would off-gas a very toxic formaldehyde, and they wanted to get away from doing this. By using a Origin 1 system and the 3955, they were able to meet all of their requirements of FST and aerospace certification, reduced weight, rapid production, and an economical way. These clamps were designed as a part of the RSO hosted Additive Manufacturing Olympics, where they used N-topology to optimize the design based on stresses in that loading environment. This provided a very, very lightweight but high strength clamp. The material has been certified with a UL 94 V0 flammability and has also been chemically tested with gas, diesel, and kerosene. They were able to build 20 parts in just over half an hour and 120 within 24 hours.
As the developers of the Origin One, we know our technology inside and out. We worked with our partners to design and print the part to get the best functional result. We're able to monitor print process data and analytics during the print to make sure everything is coming out right. We looked at a variety of materials for this application and ended up choosing two: a strong, stiff, highly chemically resistant material, and a flexible elastomer. What makes our technology special is the Programmable Photopolymerization process. P3 enables high-performance materials, exceptional accuracy, and consistency across parts.
$39.55 is built for extremely intense and extreme environments where high temperature and aerospace certification is required. The next study that I would like to look at consists of Interpro, who is a design studio. They were asked by Distech, who makes bioreactors that are desktop size, to design a motor coupler that supports their different product lines and is also strong enough to resist any forces. Being a bioreactor, it had to be sterilized and be a biocompatible material. The intent of this project was to create less than 10,000. On the right hand of the screen, I have some images of the motor couplers being used for the different SKUs in their product line. These parts print in just 2.5 hours and require 0 tooling costs. The agility of this machine and speed is a major advantage over other manufacturing methods and competitive 3D printers. This meets the biocompatibility ISO standards and provides unlimited motor configurations without the need to post-process. Helicoils are set into the part to enable rigid attachment to the motor. This is stronger than conventional ABS and again can be sterilized. The material used here was Loctite 3843, a very high stiffness, high strength, versatile material. Moving along, we have another collaboration done by F=F, who is a software-oriented company, and Slice Lab, another design studio. I encourage everyone to look up both of these companies. They make some really cool and unique products that probably only exist in a niche market. They were tasked with designing a snowboard high back, as shown on the right side of the screen. A snowboard high back needs to be extremely durable and impact resistant in order to survive the forces of the rider and any debris that may come in contact in the event of a crash. There needs to be an injection molded level of detail and lightweight. The largest goal with this company was to tweak and design high backs specifically for each of the riders and users. This enables custom feedback and very, very precise and custom fit sporting equipment. The material used has an impact strength of 73 joules per meter. It has over a 100% elongation at break meaning there's an extremely high energy absorption and rebound. For the lattice structure saves 58 grams from this high vac. When you're looking at sporting equipment or more exotic type markets, every gram matters. And the more you can save, the better you will perform. This material can be tapped and machined after printing to join up with the rest of your assembly, and it doesn't require any post-surfacing techniques. Echo Footwear, they are based out of Europe. They had the intention of printing the mold and last to be used in a direct injection process. What a direct injection process consists of is directly shooting the sole, the polyurethane sole, into the midsole. This eliminates any stitching and further assembly, reducing assembly cost, and also increasing the lifespan of the material. They are no longer bonding two different elements via stitching or glue. Instead, the polyurethane is directly shot over the midsole of that shoe. This creates a higher bond and reduces any stress concentrations around the foot. Traditionally, these molds are made out of aluminum, but with the invention, or with all of these new materials coming around, Echo thought it would be great to research the use of an Origin 1. They found that this was a very low-cost, iterative design choice that still maintained the tight tolerances and long-term durability needed. They found that products or shoes made using these molds were indistinguishable from aluminum and were able to last for over 2,000 shots. This mold and last can be printed overnight, enabling for rapid design changes and an extremely iterative landscape. This is a lower cost than CNC tooling, and by being able to print on site, they're also able to reduce any shipping lead times that may exist. There is zero visible degradation and a faster product development. Echo is a unique scenario. Well, I shouldn't say unique, but I should be emphasizing that they are harnessing the open material ecosystem as intended. They derived their own material after partnering with Henkel to achieve an end-use photopolymer, providing the results they need. This is a proprietary blend of material specific for their use case. One thing that I would like to touch on here is just because the stated HDT of a material might be lower than the plastic that you're injecting into, does not mean that you can't use it. There have been a handful of other proven use cases where the HDT is lower than the urethane or plastic being shot into it. Moving along, we have Inventus. The goal of this product was to create a portable lice removal device. It had to have exceptional surface quality, be biocompatible, heat resistant, and durable. They have high temperature steam running through this device, meaning it cannot degrade in that environment. The grips must have texture to enable easier use from the user and give an aesthetically pleasing design. The right-hand side depicts all of the parts that were printed on the Origin 1. And again, this was used with a proprietary blend of material. They already looked at what was available on the Henkel portfolio and iterated from there. A very small amount of tweaking and tuning was required, but at the end of the day, they were able to produce a product that met all of their requirements. The Origin 1 also used this to print the camera housing seen in the back. They were able to print over 100 parts in 24 hours. This made it very economical for them. And it also had a surface roughness of 2 to 3 microns, making it indistinguishable from plastic injected parts. They were able to get 40 parts in an 8-hour build, costing just over $6 per part. The parts can be stacked in the vertical direction, maximizing build space. Now I am going to jump along. I had another couple use cases, but I don't want to be holding anyone up. So I will kind of go through these really quick. We had a COVID test swab that was also printed on this machine. They were able to deliver over 500,000 test swabs and also jump between standard manufacturing and the test swab manufacturing due to the versatility by nature of this machine. You can start with one model and the next week be running a completely different model with no tooling or changeover costs like you would see in a injection molded environment or CNC environment. TE Connectivity, they are, I think, the second largest plastic injection manufacturer following Lego. They make about 192 billion parts per year. They needed to make an aerospace helicopter clamp for some electrical connectors. And as you could guess, they used 3955. This is a FST certified material. It delivered a 50 micron accuracy and 10 parts in 1 hour. It was environmentally and air tested, delivering the performance that they need.
When we set out to develop the Origin 1 3D printer, we developed a unique print process called P3 Programmable Photopolymerization that enables us to print materials that have never existed before in additive manufacturing. This has allowed us to go from prototyping to address markets and applications for end-use parts in things like aerospace, automotive, and electrical connectors.
My role at TE Connectivity is to look for new, innovative technologies. Origin really checked a lot of those off a few years ago. We have a number of Stratasys printers within TE. We have many of the FDM printers distributed throughout our organization in our plants. And we also have them in our R&D facility, some of the larger ones, some jetting technologies, and now the Stratasys Origin 1 as well. We're a global manufacturer of sensors and connector products for all industries from aerospace to appliance and automotive. Over the past 30 years, we've managed to incorporate almost every 3D printing technology into the company. With the emergence of DLP, and particularly the Origin 1 printer, we were able to print a whole range of products that we weren't able to before, both in terms of resolution, accuracy, and new materials. makes the business value really attractive. And we're anticipating many of our high mix, low volume products can be now 3D printed instead of injection molded.
We chose the Stratasys Origin 1 printer over other printers because of its reliability as well as accuracy and surface finish that we get. It's almost similar to mold injection parts. Some of our customers can't even tell the difference.
The reason we like the Origin platform so much is it enabled us to use almost any materials for our specific business units. For example, fire, smoke, and toxicity. We couldn't do this with any other platform.
We've worked with a variety of our partners to unlock material properties you don't typically see in polymer additive manufacturing. For example, extremely resilient elastomers and extremely flame retardant and tough materials.
The throughput of the Stratasys Origin 1 allows us to move closer towards series production. Years ago, we wouldn't be able to think about that as a possibility.
We make 190 billion products a year, something of that order. Where Origin 1 really helps us is to produce product at those low volumes that otherwise wouldn't have been attainable by injection molding.
The reliability of the Stratasys Origin 1 is very confidence-inspiring for us. We are very satisfied with the consistency and the repeatability of the printer.
So I've never been more excited than I am right now about 3D printing. We've got the materials, we've got the speed, we've got the accuracy. Now we're on the cusp of really getting these parts into series production, and it's really exciting.
So why was P3 brought up here? Why am I talking to you today? Why are you listening? Probably because you experience any of the problems listed on the screen. That would be a long time to part, limited and expensive materials, poor part quality, or anisotropic mechanical properties. FDM has a very low throughput and a very long post-processing attached to it. Polyjet might give extremely high resolution with realistic looking parts, but they're very low strength, brittle, and they don't perform well under UV environments. These parts cannot survive much more than 6 months to a year. If you need an end-use functional part, you need a resin that has been verified and tested to last at least 3 to 5 years. The Origin 1 meets all of those demands. FDM is anisotropic by nature, has a poor surface finish, and usually a very low accuracy, meaning you don't want to put these parts in the customer's hands. They'll probably stay within your own office or manufacturing floor. The Origin 1 provides an extremely high throughput with very compelling economics. Stacking the parts in Z allows for maximum build volume utilization. And you can print at speeds of up to 100 millimeters per hour, depending on your material. Bulk post-processing is also an option. GoEngineer provides post-processing solutions for large-scale manufacturing with additive. This is 10 times faster than traditional SLA with low-cost options. There's a broad range of high-performance materials offered by our partner companies that will continue to grow. High impact strength, high tensile strength, and high elongation at break. The average surface roughness is about 1 micron, but with tuning, you can easily get this to less than 1 micron. Tolerances as tight as 1/1000th of an inch. And large solid objects can be printed without fear of warp or inaccuracies. So when should you manufacture with P3? You need to be creating end-use parts that will be customer-facing and perform for a long time. The materials have been QUV or quick weather tested to verify that interior and exterior use is applicable. If you are printing large parts at a low volume or lots of small parts at a mid volume, Origin 1 is a great fit. If you want to do any topology optimization, lightweighting, or latticing, the Origin 1 is also able to print those geometries without any type of problem. Extremely complex, fine features, and high accuracy is where this machine excels. If you need textured surfaces, this is a really good option. Short lead times for rapid and quick manufacturing of a large material selection or large product lineup. You have a lot of different parts that you only need a few of each year, but you need a lot of different ones. This is a really good option. Plastic injection or traditional manufacturing methods aren't going to cut it if you only have a couple hundred in that volume. If you need a rapid prototype with the end-use engineering materials that still have the high accuracy and resolution to meet that end-use part, the Origin 1 will succeed. Isotropic properties, again, the strength in both X, Y, and Z, they are all equal. It's independent of the print orientation. With a extremely high accuracy, high performance material offering like this, it can reduce your tooling and molding costs or eliminate them altogether. You can print your parts or your molds at a 50 micron accuracy and typical 1 micron surface roughness. Those last two values, they can be tuned so that you can get it even tighter, but out of the box, that is what you should expect. With that, I am going to keep carrying on. If I know I've reached my 1 hour. If anybody needs to go, that is okay. But if you would like to see a competitive analysis where I show existing DLP machines, I'm going to cover that in the next 5 to 10 minutes. I'll try to keep it as quick as possible. And I will follow up with this presentation for you to look back on your own time in case you do need to go. So let's start at the very beginning when DLP was first invented by EnvisionTech back in 2002. Their first machine only had a 750 cc build volume, very, very small. And all resin that was on the market was exclusively offered by EnvisionTech. The main purpose of this machine was rapid prototyping and jewelry of very small, fine-featured parts. In 2015, Carbon launched their M1. This had a 3,600 cc build volume, or 5 times the size, with a new DLP technology called CLIP, or Continuous Liquid Interface. This vastly increased the speed and the quality of the printed parts. With that, they also presented engineering grade resins for high performance uses. The Carbon was mostly offered towards dental and small series production environments. And it did a very good job at the start. And then in 2019, the Origin 1 was released. This machine has a 7,300 cc build envelope and prints up to 3 times faster. Well, you have a 3 times faster time to part than the Carbon M1. And I say this because of the thermal cure required on carbon's materials. Carbon's materials are also a two-part resin, meaning you have a short pot life, about 8 to 12 hours that you can work with, followed by a 8 to 12 hour thermal cure in the oven. On the Origin 1, you only need a UV cure that lasts about 5 to 10 minutes, making your time to part much, much lower. The Origin 1 can also print full cross-sectional area parts, something that the Carbon and other competitors struggle with. New materials are being developed daily on this machine, and with the intent of releasing new materials each month. There is an Airbus certified resin, that 3955, which again was developed on this platform. Looking at what EnvisionTech offers today, we'll start on the left, the proprietary P4K. There is no automatic bed leveling, no heated vat, and the display is actually 2560 by 1600, even though it's listed as a 4K machine. All of the machines offered by EnvisionTech have locked materials and an RFID chip on the material canister. They do have a large selection available, but typically they are high price and low performance. The P4K has a tilting separation mechanism that is much slower than the pneumatics used on the Origin 1, and it also has a much lower build envelope. The pixel resolution varies depending on your build size, between 35 and 90 microns. The P4K is targeted most at dental and jewelry applications, whereas the Origin 1 is targeting end-use injection molded part replacement. The Envision 1 CDLM HT is an improvement to the P4K with an oxygen separator mechanism very similar to the CLP. This enables quick printing of higher performance materials. The system itself can be quite difficult to level and is lightweight. This makes it very prone to external vibrations, leading to very poor print quality. Again, the EnvisionTech has a locked material and locked settings. If you want to improve any of your process parameters or your print speeds, that is not available with the EnvisionTech machines. The pixel size is about double what the Origin 1 is, so expect about half of the accuracy on an Envision 1. There are currently 6 materials available, with some overlap between the Origin materials and the HT materials. Again, I would like to emphasize the materials were developed on this platform and then tweaked and reconfigured to work on the other machines. This isn't a direct competitor, but I'm sure a lot of you have heard about the Extreme 8K. This uses 2 4K projectors piggybacking off side by side. So it's not a true 8K, but it provides a very, very large build envelope. It's about 200K to purchase and 24K to fill that vat. So material changes are not straightforward, and you probably will have a dedicated machine or vat for each of your materials. This uses a recoater blade and a top-down process, sort of hybridizing SLA and DLP. Uses a perforated build platform, and again, quite difficult to calibrate. The pixel size on this machine is 100 microns, double that of the Origin 1. But it touts a much, much greater build envelope. Power requirements here are 220 volts only at 3-phase. They do not offer a 110 version. The fastest build rate is at about 38 millimeters per hour, so it's quite a bit slower as well. And you cannot change any of the settings to increase speed. Looking at Carbon, they recently released their M2. This follows a 3-year lease model only. So if you lease the machine, you do not actually own the machine, making it a much higher cost of ownership. The Carbon uses clip, which enables a oxygen dead zone below the printing membrane. Oxygen will penetrate through into the resin, leaving a dead zone where the resin is unable to cure. By adding this extra layer, you reduce the irradiance or the power of the projector, resulting in a lower green strength or stiffness of the part straight off of the machine. This diffused light can also lead to muddy geometries, and it also cannot handle large cross-sectional model geometries. The printable chemistries are limited to resins that are able to print in that oxygen-inhibited environment. Again, you have locked software with any printing or process parameters being conducted by Carbon 3D. You don't have control. On the Origin 1, you have full control over your printing and process parameters. There is no FST offering available on the Carbon, and most of the resins are two-part, reducing their shelf life. Parts must be cleaned immediately, or that resin on the outside will cure and permanently ruin that part's accuracy. There's a high material waste due to a two-part configuration, and due to that low green strength, you typically need to pack your parts in a sand type vessel or enclosure while post-process to prevent any warping of the part. Nexa offers the NXE 400. This is not a DLP machine. This is a LCD printer. So instead of a high power 4K projector and DMD mirror, it instead uses essentially an oversized tablet screen to cure the material. This has a much lower irradiance or power output, leading to a much lower green strength. This machine can print extremely quick with the materials they have tuned to print very quick. Nexa follows a locked material model where you can only purchase materials by Nexa, created by Nexa, and you cannot change these settings. They currently have a small material portfolio with only 10 materials available at a very, very low green strength. This results in longer post-processing time, more supports needed, and overall lower accuracy in your printed parts. The Nexa NXE 400 does not have a heated vat, meaning any of those higher performance photopolymers cannot be used here. And the 3D Systems Figure 4, this uses a 405 nanometer, again, LCD light source. So it is not a direct competitor to the DLP machines. This has a much lower irradiance, and it's only offered at full HD, not 4K. The build envelope is substantially smaller, and it has 50% lower accuracy than the XY resolution. There is no heated vat, and while they do offer a robust amount of materials, There is no FST certified, and their highest temperature, or the material with the highest HDT is a 2-part resin. The perforated head means you don't print parts directly on the platen. Instead, you have them sitting up. It also has more support involved. On the screen here are some prints that were completed on each of the machines just covered, and print time posted below. Based on these photos, we can see quite significant warping out of the Carbon 3D, Nexa 3D, and 3D systems, with the Origin 1 and Envision Tech providing the best results. These parts were then measured for their accuracy. The green represents the Z error. And I have at the very bottom underneath each of the machine names the average XY error or XY resolution. The Origin 1 outperforms its competitors at up to 6 times, ranging from 2 to 6. Here's another part that was printed on all of these machines. Highlighted in green are supposed to be some very, very tiny posts, but the only part in which those posts are evident is the Origin 1. The Nexa has very high warpage and rounding to the square corners with missing features. The Carbon has low accuracy and, again, missing features. Looking at the accuracy of that detail part, measuring the X, Y, and Z dimensions, we see a very, very similar trend where Origin 1 is 2 to 6 times as accurate with an average error of 40 microns. This is within the stated 50 micron accuracy and far surpassing what Carbon, Nexa, and Envision Tech advertise. So quick little recap. The Origin 1, it starts at 99K, uses P3 technology with 20 plus onboard sensors for analytical purposes. Very easy to use interface, over-the-air software updates, higher radiant, very, very high strength projector at true Ultra HD with a very large and expanding material selection. A heated vat and an innervable chamber provide printing materials that other machines simply cannot. Cure times are typically less than an hour on this machine, with build rates up to 100 millimeters per hour. And I apologize for keeping anyone over that, but thank you for hanging with me. And if you have any questions, I would like to open it up for a discussion. Can we get a link? Yes, I will be following up with a link to both the recorded presentation and also a raw copy of the slide deck or a PDF of the slide deck for you to go through at your own rate. All right, John, I see you have a question about, have any metal or ceramic sinterable resins been developed for the Origin One? At this, Tom, can you answer that? Because I officially don't know. I would imagine that there's something in the works or has been talked about, but that is the whole idea behind this open material platform. Is if there is a specific use case or specific application that you need to attain, by partnering with these large chemical OEMs, we will make something happen for you.
Kind of a tough question to answer. Have any metal or ceramic sinterable resins been developed for the Origin One? No, it's not a sintering type system. It's resin vat polymerization. So I guess a direct answer to your question would be no. But what we are seeing in the future, we're going to see potentially materials that have additives in them to create different properties, different types of things that are in the resins. That's very challenging to do because they're all going to affect the ability for them to receive, again, the correct wavelength and the correct intensity of light. But, people are looking for, ESD type materials in the future. There's all these things we're working on in the background that we're trying to achieve them. It just takes a while for some of these complicated things. So, John, I'm not sure I have the question. And I'll just keep talking. So John just asked about the post-processing will be required. That's one thing that is critical. We produce a technical data sheet for each of these materials. And if people follow what we call a validated workflow, then you will be able to achieve the properties that are listed on the technical data sheet. If you take a material and you try to do something different with it outside of the workflow, you're going to get different results. So we take great pride in developing these workflows so you can get really good results. So part of a validated workflow is the correct printer, the correct material, the correct settings on the machine, but also the correct cleaning of the part. And this is something that Hunter spoke to earlier, is cleaning the part, allowing the solvent to flash off a certain amount of time so there's no solvent left in the part. These are all part, and then post-curing, the right intensity of light with the right wavelength. When you print a resin, it's printing really just green handling strength. When it comes out of the vat or when it comes off the build plate, it's going to need the cleaning. It's going to need additional curing in a UV system to achieve its final properties. So there is, post-processing that is required.
Well, in case anyone has any more questions, I'll let those sort of trickle in. But I do want to show just how easy it is to get up and running with this machine. Right now, I'm removing the part that was just printed. We'll actually bring it up on camera for everyone to see. So right now, these parts are covered in resin. I need to knock them off the build plate, wash them, let them dry, and then they can be cured. Okay. When you first start this machine, it will look like it does right now. We'll have a build plate, and we just drop it into place. Again, just one bolt to calibrate. Right now, this is free to move around. Now I'm using the interface on the machine. And it is walking me through the steps I need to complete. Again, very easy, very intuitive. Started the calibration procedure. Now I'm just going to tighten that bolt. All right, that bolt is nice and tight. I'm going to hit confirm. Calibration complete. And now I'm going to take a different material. This is a black material. Doing a material change. And we're just going to drop it into place. And with that, I am ready to start printing on a different material. Yeah, let's see if any questions popped up that time. And if not, then thank you, everyone. Oh, John asked about again. Tom, are you able to follow up separately?
I am. I thought I responded back, but I'll
Okay.
put.
Okay, I
make sure
just
that you
need your response.
Yeah, just make sure that.
Into that.
Yeah, absolutely.
Okay.
Please make sure, John, that you copy Hunter on this.
Great. Well, thank you, everyone, again. I really enjoyed this. Sorry for going a little over, but I'm going to follow up with all of the links for this presentation and the PDF copy of the slides. So again, thank you, everyone.